Okay, so I have a new camera. Hopefully this works better than the old one. Okay, so we're doing two-dimensional kinematics, so it's horizontal and vertical combined. So we do a little trig in this. So let me turn on the light so we have a little better. There we go. Okay, so we do a little trig in this. So just as a reminder for SOHCAHTOA, okay? So you remember SOHCAHTOA. So, which means sine theta equals opposite over hypotenuse. So cosine theta equals adjacent over hypotenuse. And then TOA, tangent theta equals opposite over adjacent. Okay? So if I want theta from sine, I just have to do the inverse sine. So that would be the inverse sine, which is just a button on your calculator. So just so you know, like, okay, so here's sine, cosine, and tangent. So if you want the inverse of either of those, you just press second and then sine, and you get inverse sine. Or second, cosine, you get inverse cosine. Second, or tangent, you get inverse tangent. Okay, so nothing complicated there. So if you want just the theta from, and you have opposite and hypotenuse, then you could do sine theta of opposite over hypotenuse, and that would give you your theta, inverse sine of opposite over hypotenuse. Woo, words are hard. All right, so from the cosine, that would be inverse cosine of adjacent over hypotenuse. And from tangent, that would be inverse tangent of opposite over adjacent. Okay. Okay, and then you did a little bit of vector addition when you did your summer assignment. So all vectors have a magnitude and they have a direction. Okay, so they point, the head point is where the arrow is, the tail is where the arrow is not. Okay, so if you had vector A plus vector B, you would connect vector A, and then you connect vector B to the top of vector A where the head is, to tail. So then the resultant vector would be from the tail of A to the head of B. Okay, so if you did that, a lot of times you can find a right triangle somewhere in there. But anyway, so if you had an A portion maybe going up and a B portion going down, your resultant would be the hypotenuse of a triangle made with either one of them. So if I took the head of A, so if I did B one end to one end and did the tail of A to the head of B, that would be the resultant vector. And then you'd have an angle theta. This is a right triangle. And the reason that I don't know if you remember this, but if this is your theta, if you draw a line from your theta to the other side, that's your opposite. And this is the one that's touching your theta is your adjacent. Okay? So that's how we determine which side is the opposite and the adjacent. Okay? All right, so moving on. So I don't have this demonstration right this second, but I'll show you in the classroom. But one object is dropped straight down and another is simultaneously launched horizontally from the same height, which will hit the ground first. Trick question, they hit at the same time. Okay, so again, we pretend that there's no drag, there's no air resistance, we don't worry about that. But it doesn't matter if something is moving horizontally, because if nothing else is touching it, then the vertical portion, which is what time is contingent on, will be exactly the same. So if it starts in the vertical from rest, okay, at 0 meters per second, in this one, it can start it in the horizontal, but the horizontal is independent of the vertical. So your vertical is technically starting at a V0 of 0. So both of them started at a V0 of 0, so they should hit the ground at the exact same time if they're falling from the same height. Okay? Okay, and then this is just kind of a demonstration of that with some numbers to it. Now, horizontal, So the vertical portion is just free fall. The horizontal portion is constant velocity. So no matter where, like if I have a cannon on top of a cliff and it shoots and the cannon goes, right? The velocity in the horizontal is the same all the way down. The velocity in the vertical velocity here starts at 0, and for every second it gets higher and higher until it hits the ground, okay? Because in the vertical it's accelerating, because free fall means that it's accelerating. But constant velocity, your acceleration is 0. Okay? Okay, so typically for horizontally launched projectiles, we make a little chart, okay? And so just for horizontally launched projectiles, okay, your V initial and your V final in the X direction, they are the same. They are average velocity, okay? For V initial in the Y, for just horizontally launched projectiles, it's 0 meters per second. Then your V final will be some negative number in meters per second. You have no acceleration in the horizontal. The X is the horizontal. The Y is the vertical. Okay? So in the X, you're moving constant velocity, so you have no acceleration. Okay? But in the vertical, you're moving according to gravity, so your acceleration is negative 9.81 meters per second squared. Okay? Your delta X, your change in displacement, okay? For the horizontal, we call that the range. And for the vertical, we call that the height. But because it's going down, it's negative of the height. And they will fall for the same time. Okay? Now, to calculate impact velocity, okay, you will have a V final in the Y, and you will have a V average, technically, in the X. And so your impact velocity is the resultant between those. This is your V impact. Okay? And you will have an angle of theta that it makes with the ground when it strikes the ground. So I may have forgotten Pythagorean theorem on here, didn't I? I'm so silly. Okay, so you remember Pythagorean theorem, okay? It's just a squared plus b squared equals c squared, okay? That's all it is. Now, when you want to apply that here, okay, that can be your A, that can be your B, that's your C. Okay, so for your impact velocity, that's relatively easy. So your V impact is just the square root of V final in the Y squared plus the V average in the X squared. That's it. Now, your angle is a little different, okay? You will have your V final Y and you'll have your V final in the X, okay? So the V final in the Y is your opposite. The V final in the X is your adjacent. And you're looking for your hypotenuse, okay? So, I'm sorry, you're not looking for you're looking for the angle theta. So the only thing you have, I mean, you could use sine or cosine or tangent, it doesn't matter. I typically like to stick with tangent. You just stick with one thing and it works. So I do, for my theta, my theta that it impacts the ground with, I do inverse tangent of opposite over adjacent. So I do TOA, okay? So my opposite is V final on the Y over your V average in the X, okay? So whenever you report the impact velocity, that's the velocity the second before you impact, right? the instant that you impact, right? So then you have to report a magnitude, which is your impact. This is your magnitude. And direction. Your direction is the angle with which it strikes the ground. So you have to report your impact velocity in terms of magnitude and direction. Okay? Okay, so moving on. Okay, so let's talk about our graphs. So the horizontal, think of it as constant positive velocity. Okay, it might be going negative, but let's just, for ease of making these graphs, let's call it constant positive velocity. So my x versus t, okay, it's going constant positive velocity, so it's just a straight line in the x versus t. The v versus t, it's going a constant velocity. So if it's positive, it's going to be a flat line here. If it were constant negative, then this line would it'd be straight, but it'd have a negative slope. So it would be going this way, and this one would be on the bottom. The a versus t is the easiest, because if it's going constant velocity, it's not accelerating, so it would be just darker on the 0. Okay? Now, vertical motion, it's in free fall. So if it's in free fall, then your x versus t graph is going to have no slope, like 0 slope, going to a negative slope. So no slope would be 0 to a negative slope. So it's a parabola, or half a parabola. And then your velocity versus time, your velocity is basically always negative because it's falling below like a cliff or a place. It's falling below that. So that would always be from 0 to a negative number. So it's going to have a negative slope line, but it's going to be straight. And then your acceleration versus time, well, acceleration is always due to gravity. So it's going to just be a line in the negative quadrant, because that's where negative 9.81 or whatever the gravity is on that particular place, planet, moon, whatever. Okay? So again, horizontal graphs, constant positive velocity. Vertical graphs, they are constant negative acceleration, but in the negative quadrant for the velocity. Okay, so let's look at our example. Okay, so we have a diver initially moving horizontally with a speed v, dives off the edge of a vertical cliff and lands in the water a distance d from the base of the cliff. How far from the base of the cliff would the diver have landed if the diver initially had been moving horizontally with a speed of 2v? Okay, so here's my cliff and here's the water below. Okay, so we're saying she dives off with v, okay, and ends up at d away. Well, if it's the same cliff, then it's going to have the same height, right? It says she's moving with the speed of this vertical cliff. How far from the base of the cliff? Same cliff. I assume it's the same cliff, okay? Would the diver have landed if the diver had initially been going with a speed of 2v? So if she's going v, then if she's going 2v, let me get a different color. Maybe pink will show up. If she were going 2v, then where would she end up? Okay, well, think about if you're going horizontal, okay, then the range is dependent on the time, but the time to drop is going to be the same for both of them. So it's going to have the same t for both the v and the 2v. Okay, so what's different? Average velocity equals your displacement over time. So in this case, v equals d over t. Okay, so if we have 2v, it's going to have to be 2d if the time is the same. So it has to be twice the range. So it's c, 2d. Okay? Okay. Because in the horizontal, if they have the same exact time, and the horizontal is only dependent on velocity and time, that's your horizontal displacement, then if you double the velocity but keep the time the same, then you double the range. This is the range, okay? All right, moving on. Practice review. Okay, you have a truck traveled 400 meters north in 80 seconds. Then it traveled 300 meters east in 70 seconds. The magnitude of the average velocity, okay? So we have north 400 meters in 80 seconds. Then east, no, I didn't mean to draw my vectors like that. Sorry, it's fine. They're off scale, so maybe it stops about maybe here. Look at me, I've got white out. You probably don't, sorry. Cool, there we go. And then 300 meters for 70 seconds. And I want to know the magnitude of the average velocity. Okay, so there's a couple ways I can do this. Okay, so since, time is not really a vector, but the displacement is. So what you want to do is find the hypotenuse of these vectors, the 400 and the 300, and then divide it by the total time. Okay, so so then it would be the square root of 400 squared plus 300 squared, and then all of that over 80 plus 70, which is 150 seconds. Okay, and it's a 3, 4, 5 right triangle. I don't know if you can see that, 300, 400, so this must be 500. So it'd be 500 over 150, so 500 meters over 150 seconds, which would give you 3.3 meters per second. So that's B. Okay? So you can't use the time in the vectors. You really can't. That's just information that I put there, but it's not part of the vector. The vector is really only the displacement, the positive 400 north and the positive 300 east. So then you went a magnitude of 500 meters. That's from point A to point B. Okay? So then that divided by the total time is your magnitude of the average velocity. If they'd wanted average speed, that'd be a different type of question. Okay? Anyway, okay, so there's that. Moving on. Oh, well, let me do just a quick example question. I didn't realize there's no example question in your notes packet. Okay, so here's a pretty standard example. I just kind of made this up. This is just for the math portion. You have a bowling ball, rolls off a 150-meter cliff with a velocity of 10 meters per second. I want to know how long is it in flight and what is the range. So first I'm going to make me a little chart, right? So I'm going to make a little chart with my X and my Y and my V naught, V, A, delta X, and T. So in the horizontal, I know it's leaving with a velocity of 10 meters per second, so technically this is 10. This is also 10. My acceleration is 0. I'm looking for the range, and I'm looking for how long it's in flight. For the Y, it's rolling off of the cliff. So in the Y, just the vertical direction, it's just falling. So it's like 0 meters per second for the beginning. I don't know the impact. Oh, that's a good thing. I'm going to do C. What is the impact velocity? Okay, so that's going to be a part C. All right, so I'm going to have to know that. And then my A is negative 9.81 because it's not touching anything. It's only having gravity. And then it's 150 meters cliff, so my Y direction is negative 150 meters, and I'm looking for time. So it looks like I can use the Y information to find the time and the V final. So for part A, let's find time first. So using just the Y data, because Y is independent from X, do not cross-contaminate them, okay? So for my Y, my V naught is 0, so I can say my delta X equals V naught T plus AT squared over 2, and my V naught is 0, so that goes away. So then my A is just negative 9.81, looking for my T squared over 2, and that equals my negative 150. So rearrange, your T equals 2 times negative 150 over negative 9.81, and we square root it. Come here, calculator. Okay, so plug that in. And we get 5.53 seconds. So that's how long it falls. That's not too bad. So that's part A. Part B, I want to know the range. Out of water. All right, part B, I want to know the range. So now that I know the time, and it's going at constant velocity equals displacement over time. So I just multiply both sides by time, and it gives me my displacement. So 5.53 times 10 is 55.3 meters. So that's my range, that's my displacement in the X direction, that's my range, okay? All right, then the last part I want to know is my impact velocity. Well, my final velocity in the X is pretty easy, because it's 10. Because it's 10 at the beginning, it's 10 at the end. So, because it's constant velocity. So now I need to find the velocity in the Y direction. So, I'm just going to use the acceleration equation, because now I know my V initial, I know my A, I found my time, it's just easier to do that. So my A equals V final minus V initial over time. My V initial was 0, so I multiply both sides by time. So 5.53 times negative 9.81. Negative 54.25 meters per second. Okay, so that's my final velocity in the Y. I want to know my impact. So my V impact is the square root of V final in the X squared plus V final in the Y squared. So that's 10 squared plus negative 54.25 squared. And I get 55.2 meters per second. And now I need to know my angle. So my angle, theta, is inverse tangent of V final in the Y over V final in the X. So that's inverse tangent of negative 54.25 over just 10. There we go. My bad. Okay. Okay, oops. Oh, and you have to make sure your calculator is in degree mode to do this. So, like mine is right now in radians, you need to put it in degree mode, or else it'll give you your answers in radians, and you don't want radians, you want degrees. All right, so negative 79.6 degrees. So, your impact velocity is 55.2 meters per second at negative 79.6 degrees. Okay, and that is one question from start to finish for an example. Okay, good luck. Have a great rest of your night.